Hello there, and welcome to another in a series of videos about limits in calculus. In a previous video, I talked about infinite limits, in the sense that you can sometimes have the limit of some function as x approaches some number turn out to be infinity. But in this video, we're going to talk about the limit of some function as x approaches infinity, or as x approaches negative infinity. So we'll talk about what that means and how to figure out what a limit like that would be, how to evaluate those kinds of limits. So I'm going to start with an example or two, an application sort of thing, where you might use limits like that. Suppose the concentration of a drug in a patient's bloodstream, t number of hours after the drug is administered, is given by the function c of t equals 0.2t divided by t squared plus 1. Now, I have no idea how close this comes to what would actually happen in the real world. And in any case, any mathematical formula or model like this is only an approximation at best to what happens in the real world. But pretend for the sake of this example that that's what happens. The point of this example is not the science, but the mathematics behind what's going on with this formula. So after half an hour, if I plug in 1/2 or 0.5, it shows that the concentration is 0.08. After 1 hour, it's 0.1. And that, if you look at the graph, is the highest that it gets. After 1.5 hours, it's back down to 0.09 something. After 2 hours, it's back down to 0.08. After 3 hours, it's 0.06. 4 hours after the drug is administered, it's 0.047 something. After 5 hours, after 6 hours, after 12 hours, after 24 hours, after 48 hours, after 100 hours, after 1,000 hours. Oh, now it started to give it to me in scientific notation, but it's a very, very small number. And you can see on the graph that as we plug in larger and larger numbers into this formula, the values we get out get smaller and smaller in the sense of being closer and closer to 0. So what that's telling us is that in the long run, the concentration of the drug will never quite reach 0. Now remember, I said this was only an approximation to what happens in the real world, but if this model was exactly right to infinite precision, that would mean that the concentration of the drug in the bloodstream would never completely disappear. It would never quite reach 0, but it will eventually get below 0.01. If you wait long enough, it will eventually get below 0.001. It will get below 0.00001. It will eventually get below 0.0000001. And I could keep on going. No matter how small a number you give me, as long as that number is positive, I can go forward to a time when the concentration of the drug gets below that very, very tiny number and stays there. So we can say that the limit as t approaches infinity of 0.2t divided by t squared plus 1 equals 0. So by that we mean that as t just gets bigger and bigger and bigger and time goes further and further into the future, the value of that function, the concentration of the drug, is approaching, getting arbitrarily close to 0. Here's another example. Suppose the total worldwide box office receipts for a movie in millions of dollars, X months after its release, are given by the function t of x equals 150x squared divided by 2x squared plus 3. So you plug in a number for x, and that'll tell you after that many months how many millions of dollars the movie has made. So again, we could investigate what's going on by plugging in some numbers. After 1 month, it's made $30 million. You can plug in 2 and see that after 2 months, it's made a little more than $54 million. After 3 months, it's up to 64 point some million dollars. After 4 months, 5 months, 6 months. What about after 12 months, 1 whole year? It's up to 74.226804. What about after 24 months? That is 2 years. Now it's up to 74.8 something million dollars. 5 years would be 60 months, and then it's up to 74.9687763 million dollars. If I stick in 100 or 500 or 1,000 for the number of months, the number we get out of this function, the number of millions of dollars it's made, it keeps getting bigger, but there's a limit to how big it gets. It never gets any bigger. It always stays a little bit smaller than 75. And as we go off to the right on this graph, as the x-coordinates get bigger and bigger and bigger, the y-coordinates are leveling off. They keep getting a little bit bigger, but not by very much. They're leveling off and getting really, really close to 75. So we can say that the limit as x approaches infinity of 150x squared over 2x squared plus 3 equals 75. There isn't an actual number that I can plug in and get exactly 75. Remember, infinity is not a number that you can plug in for x, but I can plug in a number like 1,000 or 1,000,000 or 1,000,000,000. And what I get is not quite 75, but really, really close to it. So I can get as close as I want to 75. I just can't get precisely equal to 75. So when we talk about what happens as x approaches infinity, we mean that x gets arbitrarily large as you want, or larger than that, or larger than that. Some examples. The limit as x approaches infinity of x plus 2 would be infinity. If x is arbitrarily large, then x plus 2 gets arbitrarily large. There's no limit to how big that can get as long as the number you put in for x itself is big enough. And remember, to say that the limit of something equals infinity is saying that that limit does not exist, because we can get values of that function that are bigger than any particular number. Bigger than 1,000,000, bigger than 1,000,000,000, bigger than a quadrillion. The limit as x approaches infinity of the function square root of x is infinity. If x can get arbitrarily large, the square root of x can get arbitrarily large. There's no limit to how big that can get. On the other hand, the limit as x approaches infinity of 10x over x is just 10, because no matter how big a number x is, if you take 10 times x and then divide by x, that's always just 10. So 10 times a really, really huge number divided by that very same really, really huge number is always just going to give you 10. So that's what that limit is. And if you want to know the formal definition, in previous videos I've explained the formal definition of what it means to take the limit of some function as x approaches some number, c. It means that you can get values of f of x that are as close as you want to that limit L by making sure that the number you put in for x is close enough to that number c. Well, now we're talking about, instead of x approaching a number c, we're talking about x approaching infinity. And so to say that the limit as x approaches infinity of f of x is L means that you can get values of f of x to be as close as you want to that limit L by making x large enough. So x isn't getting close to some particular number. Instead, it's getting large, and it can be larger than any particular degree of largeness you want. And then for x to approach negative infinity would mean that x gets arbitrarily, well, I got to be a little bit careful here, because when we talk about numbers being small or smaller than other numbers, we could mean small in the sense of they're small in absolute value, they're close to zero, or we could mean that they are negative numbers, and in that case, one number being less than a number means it's more negative, but that makes it larger in absolute value. So x approaching negative infinity, think about numbers like negative 1,000, negative 1,000,000, negative 1,000,000,000, negative some really, really huge number in absolute value, but negative. So we're going away off to the left on the number line. So the limit as x approaches negative infinity of x plus 2 would be negative infinity. If x is a really, really negative number, so is x plus 2. Like if x is negative 10 billion, x plus 2 would be negative 9,999,999,998, which is still very negative. And you can get x plus 2 to be even more negative than that just by making sure the number you put in for x is negative enough. The limit as x approaches negative infinity of x squared would be positive infinity. Remember, if x itself is a negative number, x squared is going to be positive. And the bigger x is in absolute value, the bigger x squared is. So like if x is negative 1,000, x squared is positive 1,000,000. There's no limit to how big that can get. The limit as x approaches negative infinity of 10x over x, again, that's just 10. Because no matter how big or small or negative or whatever x gets, 10 times x divided by x is always just going to be 10. What about the limit as x approaches infinity of x over x plus 1? That is, what happens when you take a really, really big number and then divide that by the number that's one bigger. 10 divided by 11, or 20 divided by 21, or 999 divided by 1,000, or 999,999 divided by 1,000,000. Those numbers are getting closer and closer to 1. No matter how big a number you put in for x, x divided by x plus 1 is always going to be less than 1 by a little bit, but it's going to get close to 1. Hopefully you can see that from these calculations. This column shows them in fractional form, this column shows them in decimal form. And here's the graph of the function x over x plus 1. And x approaching infinity is like saying what happens as we go off sort of forever to the right. The graph seems to be leveling off. And the points on the graph with really big x coordinates all have y coordinates that are really close to 1. So that's what the limit is. The limit is 1. What about if we just had 1 over x plus 1 and took the limit of that as x approaches infinity? Now we're getting numbers that are really, really close to 0. So the bigger x is, the bigger x plus 1 is, and the smaller, that is the closer to 0, 1 over x plus 1 is going to be. If x is a really big number like 999,999, then 1 over x plus 1 would be 1,000,000th, or 0.000001, which is just a little teeny bit bigger than 0. And if x gets even bigger than that, 1 over x plus 1 gets even closer to 0 than that. And as the graph goes off to the right and the points on the graph get bigger and bigger x coordinates, their y coordinates get closer and closer to 0. So the limit there is 0. And can you see what the limit would be as x approaches negative infinity of 1 over x? So x is approaching negative infinity, which means the numbers we're putting in for x are very large in absolute value, but negative. Negative 1,000,000, negative 1,000,000,000, negative 999,999, things like that. 1 over a number like that Well, since x itself is negative, 1 over x is negative, but it's very, very close to 0. It's a little bit less than 0, but the more negative x gets, the bigger x gets in absolute value, the closer to 0 1 over x gets. So the limit there is 0, and you can see that on the graph because x approaching negative infinity is like going off to the left. And the points on the graph with the very negative x coordinates all have y coordinates that are very close to 0. So as x approaches either positive infinity or negative infinity, the limit of 1 over x is 0. The bigger the denominator gets, the closer to 0 1 over that denominator gets. And that would still be the case if instead of just 1 over x, we had 1 over x to some positive power, like 1 over x squared, or 1 over x cubed, or 1 over x to the 10th. It works out really nicely if the power is a positive integer. If the power is a positive number that's not an integer, then you might run into trouble if x is a negative number, because negative numbers to, for example, the 1/2 power would be like the square root of a negative number. That's undefined if you're just working with real numbers. But so it's not quite as simple as saying that the limit is always 0 for any positive power. But if you're talking about x approaching positive infinity, then you can say no matter what the power is, as long as it's x to any positive power, the limit of 1 over x to that power is 0. And it would still be 0 if instead of a 1 on top you had any other particular constant. So the limit of any constant over x to the p power is 0. And these all can be proved. I'm not going to prove them here, but hopefully they make sense. They look like they should be true. And in fact, anytime you have an expression that's made up of a numerator over a denominator, a function written in fractional form, if the denominator approaches either positive or negative infinity, and the numerator does not, that's enough to tell you that the limit of the whole thing has to be 0. If you have a number on top, and then you're dividing it by a really, really big number on the bottom, at least big in absolute value, you're going to get a really, really small number as a quotient. And the bigger that denominator gets, the smaller, that is, the closer to 0, the quotient gets. Now, on the other hand, if the denominator and the numerator both approach positive or negative infinity, then just from that, you can't tell what the limit of the whole thing is. You've got a really big numerator divided by a really big denominator. What do you get? Well, it depends on which one's bigger and by how much and that sort of thing. So the limit of the whole thing, numerator over denominator, could turn out to be 0, could turn out to be infinity, could turn out to be 10 or 1 or negative 17 or any other particular number. It just depends on what the function is and what specifically happens. And we talked about how as you go off to the right or to the left, the graph levels off so that points on the graph with really, really big x coordinates have y coordinates that are really, really close to, well, 1 in this example. And so the graph is leveling off and becoming asymptotic to that straight horizontal line. That is, that line, y equals 1, is a horizontal asymptote for the graph of that function. Remember, an asymptote is a straight line that a curve approaches. So the graph of this function never completely straightens out, but as you go further and further off to the right or to the left, it looks more and more like it's just a straight line. That particular straight line, y equals 1. Now, let's evaluate some limits. Let's see how to find what the limit of something is as x approaches infinity. What's the limit as x approaches infinity of 3x minus 7 over x minus 4. So if x is a really, really big number, then on top we get 3 times a really, really big number minus 7. That's going to be big. A really, really big number minus 4. That's going to be big. And I think the number on top is going to be approximately 3 times as big as the number on the bottom. Not exactly, but approximately. So that when we divide, it should come out to be approximately 3. But here's how we can see exactly what's going on. We can take that fractional expression and divide its numerator and its denominator both by x. Or if you'd rather, you can think of it as multiplying the numerator and denominator both by 1 over x. That's a legal thing to do. You can take any fractional expression and multiply or divide the numerator and the denominator both by the same factor. So I'm dividing the numerator and denominator both by x, or multiplying by 1 over x, which means now we have 3x over x minus 7 over x on top, and x over x minus 4 over x on the bottom. Well, 3x over x would just be 3, and x over x would just be 1. So now we're looking at the limit as x approaches infinity of 3 minus 7 over x over 1 minus 4 over x. Now if x is approaching infinity, 7 over x would be approaching 0. Remember we said 1 over x, or 1 over x to a positive power, or any other constant over x to a positive power would have a limit of 0 as x itself approaches infinity. Same thing with the 4 over x on the bottom. It is also approaching 0 as x approaches infinity. So if we take the limit as x approaches infinity, we get 3 minus 0 on top over 1 minus 0 on the bottom. So that would be 3 over 1, or just 3. So the limit is in fact 3. The bigger x gets, the closer 3x minus 7 over x minus 4 gets to just being 3. And the graph looks like this. As we head off to the right, the graph levels off, and points on the graph with really large x coordinates have y coordinates that are really close to 3. And so that line, y equals 3, is a horizontal asymptote for the graph of the function 3x minus 7 over x minus 4. How about the limit as x approaches infinity of 4 million over the square root of x minus 17? Now that's a really big numerator, but eventually the denominator is going to get even bigger than the numerator. The numerator is just staying there at 4 million, but the denominator is getting bigger and bigger and bigger, and in fact going to infinity. So eventually we're going to have 4 million on top divided by a number on the bottom that's so much bigger than 4 million that when we divide, it's going to come out close to 0. So this is a situation where the denominator is approaching infinity and the numerator is not, and so the limit is going to be 0. And we could do that same trick we did in the last example, divide the numerator and the denominator both by the same expression. In this case, if I divide on top and on the bottom both by the square root of x, then we get a numerator that would be approaching 0, because it's a constant over x to the 1/2 power, or the square root of x, so that would be approaching 0. And then on the bottom we have square root of x divided by the square root of x is just 1, minus 17 divided by the square root of x, which would have a limit of 0. So the limit is 0 on top over 1 minus 0, which would be 1 on the bottom, and 0 divided by 1 is 0. So yes, the limit is 0. As we go off to the right, the graph flattens out and approaches 0. So the line y equals 0, otherwise known as the x-axis, is the horizontal asymptote. Now what about this? The limit as x approaches infinity of 6x squared plus 2x plus 1 over 2x squared plus x minus 7. Well, this time I'm going to divide the numerator and the denominator each by x squared, or multiply by 1 over x squared, if it's easier to think of it that way. So 6x squared divided by x squared would just be 6. 2x divided by x squared would reduce to 2 divided by x. Cancel out the x on top with one of the two x's on the bottom. And then 1 divided by x squared would just be 1 over x squared. Meanwhile, down here, 2x squared divided by x squared would just be 2, plus x divided by x squared simplifies to 1 over x, minus 7 divided by x squared. And now we take the limit as x approaches infinity, and then everywhere we have a constant over x to a positive power, that's going to 0. So the limit we get is 6 plus 0 plus 0 on top over 2 plus 0 minus 0 on the bottom. So that would just be 6 over 2, or 3. So the limit is 3. If we take this function and plug in a really, really big number for x, we get a value that's really, really close to 3. And as the graph goes off to the right, it levels off and approaches this horizontal asymptote, the line y equals 3. Now what about this one? The limit as x approaches infinity of x squared minus x plus 5 over 3x cubed minus 2. I'm going to divide everything on top and on the bottom by the same thing, x cubed. Or you can think of it as multiplying through by 1 over x cubed. So on top, that gives me x squared over x cubed, which simplifies to 1 over x, minus x over x cubed, which simplifies to 1 over x squared, plus 5 over x cubed. And on the bottom, 3x cubed over x cubed would just be 3, minus 2 over x cubed. Now we take the limit as x approaches infinity, and everywhere we have a constant over x to a positive power, that's going to 0. So the limit is 0 plus 0 plus 0 on top over 3 minus 0 on the bottom. That would be 0 over 3, which is 0. So this time the limit turned out to be 0. And the graph does level off and approach 0 as we go off to the right. The horizontal asymptote is the line y equals 0. That is, it's the x-axis. By the way, if we wanted the limit as x approaches negative infinity, everything else would work exactly the same. That limit would also be 0. For any rational function, like the ones in these last few examples, the limit as x approaches positive infinity and the limit as x approaches negative infinity can both be found the same way, and they will turn out to be the same number if it actually turns out to be a number. Now, what about the limit as x approaches negative infinity of x to the fourth plus 7x over 5x to the third minus 9? I'm going to divide the numerator and the denominator both by x cubed, or you can think of it as multiplying by 1 over x cubed. Remember, we are allowed to multiply the numerator and the denominator both by the same thing. So when we do that, it simplifies to x to the fourth over x cubed would be x, plus 7x over x cubed simplifies to 7 over x squared. And on the bottom, 5x cubed over x cubed is 5, minus 9 over x cubed. Now, as x approaches negative infinity, this x here, it's approaching negative infinity. The 7 over x squared is approaching 0, and the 9 over x cubed is approaching 0. And we have a numerator that's approaching negative infinity plus 0, which would be negative infinity, over a denominator that's approaching 5. And so that limit would be negative infinity. In other words, the limit doesn't exist because as x itself gets more and more negative, we get values of this function that are more and more negative. Now, the strategy I was using here and in all of these recent examples was to divide the numerator and the denominator both by the highest power of x in the denominator. So here, that highest power of x in the denominator was x cubed. You might wonder, would it have worked to divide the numerator and denominator both by x to the fourth power, the highest power of x in the numerator? Well, sort of. We would have gotten a 1 on top, and we would have gotten everything on the bottom going to 0. And so we would have had a limit of 1 in the numerator over 0 in the denominator, and that would be enough to tell us that the whole thing just does not exist. But it would be a little tricky to specify whether the limit was positive infinity or negative infinity, because we'd have to figure out, is it positive or negative if x itself is a very negative number? So by dividing the numerator and denominator both by the highest power of x in the denominator, that makes it easier to tell whether that limit is negative infinity, like it is here, or whether it would turn out to be positive infinity. In any case, here's what the graph of this function looks like. And you can see that if we were going off to the right and x were approaching positive infinity, that limit would be positive infinity. But since we were going off to the left and letting x approach negative infinity, the graph is headed downward, and there is no limit to how far down it goes. That limit is negative infinity. We can get values of this function as negative as we want, as small in the sense of being very large in absolute value, but negative, just by plugging in very negative numbers for x. Now notice in this last example, we were looking at the limit of a rational function as x approaches either positive or negative infinity. When the degree of the numerator is greater than the degree of the denominator, like in this example, we get a limit of either positive or negative infinity. The limit does not exist. There is no horizontal asymptote. And you can kind of see why. We get the kind of thing happening that happened in this example. On the other hand, remember what happened here where the degree of the numerator was smaller than the degree of the denominator. 2 on top versus 3 on the bottom. Then we got a limit of 0. And that always happens when you have a rational function where the degree of the numerator is less than the degree of the denominator. Then the limit as x approaches either positive or negative infinity is 0. And the x-axis is a horizontal asymptote for the graph of that function. And we saw another example of that early on in the video when we were looking at the expression or the function 0.2t over t squared plus 1. There we had a numerator with a degree of 1 over a denominator with a degree of 2. So the degree of the numerator was smaller than the degree of the denominator, and the limit as t approaches infinity turned out to be 0. And we were looking at some examples where the degree on top and the degree on the bottom were the same. So when you're looking at a rational function where the degree of the numerator is equal to the degree of the denominator, then the limit as x approaches either positive or negative infinity is the leading coefficient of the numerator over the leading coefficient of the denominator. In other words, you look at the coefficients on those highest powers of x. Whatever that number is on top, divided by whatever that leading coefficient is on the bottom, that gives you the limit for the whole rational function. And then y equal to that limit gives you your horizontal asymptote. So in this example, the numerator and the denominator were both degree 2. They had the same degree. So the leading coefficient of the numerator was 6. The leading coefficient of the denominator was 2. And by taking 6 over 2, we got our limit of 3. We saw another example of that early on in the video. we were looking at the function 150x squared over 2x squared plus 3. So there, the numerator and denominator had the same degree, 2, and we had a leading coefficient of 150 on top over a leading coefficient of 2 on the bottom. 150 divided by 2 is 75, and that's what that limit was as x approached infinity. Let's try another example. Taking advantage of this fact here, if we want the limit as x approaches negative infinity of 50 minus x plus 14x to the fifth over 9x squared plus x cubed minus 2x to the fifth, this is a rational function. It's got a polynomial on top over a polynomial on the bottom. The degree of the numerator is 5, because that's the highest power that x gets raised to on top. The degree of the denominator is also 5. That's the highest power that x gets raised to on the bottom. The leading coefficient of the numerator, that would be the coefficient on that highest power of x, is 14. And the leading coefficient of the denominator, the coefficient on the x to the fifth power term down there, is negative 2. And so the limit is 14 divided by negative 2, which is negative 7. So the limit as x approaches negative infinity, and it would be the same if we wanted the limit as x approaches positive infinity. Either way, that limit is negative 7. As we go off to the right or to the left, the graph levels off and approaches that straight line, that horizontal asymptote, y equals negative 7. If we take this expression and put in a number for x that's really, really large in absolute value, but either negative or positive, the value we get out is going to be very close to negative 7. A few other limits worth knowing. The limit as x approaches infinity of e to the x is infinity, and the limit as x approaches negative infinity of e to the x is 0. Now, the function e to the x always gives you a positive value, no matter what x is. If x is a really big positive number, e to the x is really, really big. If x is a really negative number, e to the x is still positive, but only by a little bit. It's only a little bit bigger than 0. So if you look at the graph, as we go off to the right, it shoots way up. And as we go off to the left, it levels off and approaches the x-axis. What's the limit as x approaches infinity of e to the 1 over 5x plus 1? Well, 1 over 5x plus 1 itself would be approaching 0 as x approaches infinity. We got a constant numerator over a denominator of degree 1 going to infinity. So that would be approaching 0. And then e to that would be approaching e to the 0, which is 1. Now the limit as x approaches infinity of e to the 5x plus 1 would be infinity. The bigger x gets, the bigger 5x plus 1 gets, and the bigger e to that number gets. And the limit as x approaches negative infinity of e to the 5x plus 1, well, that limit would be 0. If x is approaching negative infinity, 5x plus 1 would be approaching negative infinity, and e to something that's going to negative infinity would be going to 0. One way you can think about this is you could think e to the negative infinity would be like 1 over e to the positive infinity, which would be like 1 over infinity, which would be 0. So when I write it this way, I'm not being strictly mathematically correct by saying things like 1 over infinity equals 0, but it gives you the idea of what's going on. It's kind of a shorthand way of saying the limit of 1 over something that's approaching infinity would be 0. What about the limit as x approaches infinity of the function sine of x? Well, all we can say there is that limit just does not exist. If x is a really, really, really big number, well, it depends on what big number it is. There are some big numbers where the sign of that big number is 1, and others where the sign is -1, and others where the sign is 0, and others where the sign is something else in between. As we go off to the right, the graph of the sine function just keeps wiggling up and down and up and down. It never levels off or approaches any one particular value. So the limit does not exist. Same thing with the limit as x approaches -infinity, going off to the left. That limit does not exist. And we could say similar things for the other trigonometric functions. The limit as x approaches infinity of cosine x or tangent x does not exist. One limit that does exist is the limit as x approaches infinity of the arctangent function, the inverse of the tangent function, and that limit is pi/2. If you take the arctangent of a really, really, really big number with your calculator in radians mode, you get a value that's really, really close to pi/2. And as x approaches -infinity, the limit of arctangent of x is -pi/2. Now, to kind of sum up, this is the 7th in my series of videos about limits. First video was an introduction to the idea of limits and how to find them graphically and numerically. Then I had a video on how to find limits analytically, doing some algebraic manipulation on how the function's defined in the formula and that sort of thing. Then I had a video on the formal delta epsilon definition of a limit and how that works. I had a video on one-sided limits, the limit as x approaches some number from the right or from the left. I had a video about infinite limits, like where the limit of something equals infinity or equals -infinity. I had a video about continuity, what it means for a function to be continuous and how that relates to or is defined in terms of limits. And then there was this video, limits as x approaches infinity or as x approaches -infinity. So is that it? Is that all there is to say about limits? Well, if you were taking a calculus class, this would probably be the end of the chapter on limits, and then you would go on to the next topic, which would probably be derivatives. So this would be sort of it for now. But there is more that you can say about limits. There would be more that you would eventually get to in terms of limits, like other calculus concepts like derivatives and integrals are defined in terms of limits. If you take enough calculus, you will probably eventually encounter something called L'Hopital's rule, which is a way of using derivatives to help you evaluate limits of the form 0/0 or infinity/infinity. So if you're looking for the limit of an expression where the numerator and the denominator both individually approach 0, you can use something called L'Hopital's rule in many cases to be an easy way of figuring out what the limit is. But since that involves derivatives, you don't meet L'Hopital's rule until after you've learned all about derivatives and how to find them. It might not show up until the second semester of calculus, if you're taking the calculus sequence. And there are other so-called indeterminate forms, like 0 times infinity, or infinity minus infinity, or 0 to the 0. And what it means for those to be indeterminate forms, that means if you're talking about the limit of some expression that's made up of one part that's approaching 0 times another part that's approaching infinity, or one part that's approaching infinity minus another part that's also approaching infinity, or one part that's approaching 0, but then it's being raised to a power, and that power is also approaching 0. Just knowing that does not tell you what the limit of the whole thing is. It could be 0, it could be infinity, it could be something in between. It's indeterminate. So you would have to do some more work, some more analysis or manipulation, or be kind of clever or do something to it to figure out what the limit of that particular function was. So that's more advanced or trickier limits that you might study further on down the line. A topic that comes up probably in the second semester of the calculus sequence is infinite sequences and series. And you would have to know about limits both to understand how those are defined and also to do some of the things that you do with infinite series. Some of the convergence tests that you use to figure out whether a particular infinite series converges or diverges involve evaluating some limits, often limits as the variable approaches infinity. And this is something that probably you would get to in the third semester of a calculus sequence, but you would investigate limits of functions of more than one variable. Suppose you have a function of x and y, and you want to know what's the limit of that function as xy approaches some particular point or pair of numbers, a, b. And this can be a lot more complicated than one-dimensional limits, because with a function of just one variable, you can talk about x approaching a particular number from the left or from the right, but those are the only ways you can approach a number in one dimension. But if you're in two dimensions and you're talking about a point in the xy plane approaching some particular x and y, some particular point, there's all sorts of different directions you can approach from and all sorts of different paths you can take to approach a particular pair of numbers. And that can make two-dimensional limits or limits of functions of two or more variables more complicated. So that's something you would encounter probably in Calculus 3, probably in the third course or semester in the calculus sequence. So this is the end, at least for now, of my series of videos on limits.